Hi, everybody. If you don't know me, my name is Justin Fournier. I teach physics at Cypress High School, and I'm really excited to show you guys what we at the course lead team came up with for the class of Physics in the Universe at Anaheim Union High School District. So, yeah, you're going to see actually that it looks a lot like the California framework. We just modified a couple of things and based kind of off of two criteria. One, if it just made sense to us to fit it in this and organize it in this fashion, or two, if it better fit our students at Anaheim Union High School District. So I'm really excited to show this to you. Let's see what it looks like. So how this is going to work is that I'm actually going to start by giving you just kind of an overview of what it is that what the course titles are and that. And then I'm going to go into a little bit more detail to show you what each one of those instructional segments look like. And then I'm going to review again those instructional segments, and that'll be it. So let's go into this. So here is a document that will be shared with you that you can see. We got 8 units here. Before we go any further, I'd like to preface this video by emphasizing a couple of things. First, this video walks through the content outline. However, there's still work to be done on selecting real-world phenomena or problems to drive the storylines of our instructional segments and create student-centered, sense-making opportunities throughout our instructional segments. We recognize that emphasis of the NGSS is providing this space for students to construct and revise explanations behind the how and why of the way things work and interact in our natural and human-made world. Our three-dimensional standards are beyond the content and ideas in this video, as they include the science and engineering practices and cross-cutting concepts which require the student to actively engage in the nature of science. Secondly, this video is only offering the scope and sequence of the Physics in the Universe course at AUHSD in the material, content, and ideas that should be addressed in the first and second semesters. While we will be providing example storylines for teachers to use in the coming months, teachers at AUHSD have the creative freedom to pursue storylines that may better fit their students as long as they fit in the scope and sequence we have laid out. All right, back to the video. Let's go look at what instructional segment 1 looks like. So segment 1 is describing motion. When I start off the year, I'll usually start off with having my students gather around in a circle, and we push essentially what's like a large air hockey puck. It's got a fan on it and everything, and you start with the fan off. You push the puck, and the puck slowly comes to a stop, right? And you ask, why would the puck come to a stop? And typically some student will answer, oh, it's because of friction. Yeah, because of this force of friction, right? And if you want to really understand motion and how it works, you want to get rid of this frictional force. So you turn on the fan then, and you have students then push the puck with the fan on, and it moves in essentially a frictionless environment. And then you ask them, make some observations. What do you notice? And when the students start to wonder, then as they're pushing this puck, they start to realize, patterns that they're noticing of the motion and things like that. Then you ask them to try and come up with what they would think of like some laws for motion. And typically the majority of groups will come up with that this thing has to go that the object goes in a straight line unless I push it, right? And then when I push it, it changes its motion and goes the other direction. Then it just keeps going in a straight line. Then I push it and it goes the other direction. So most students end up getting that. And what's great there is already they got Newton's first law of motion and they got Newton's second law of motion in a qualitative sense, right? So then you ask them, well, what about being able to make predictions off of this? How could we maybe compute these quantities that you figured out qualitatively. This is addressing HSPS 2-1, right? Which is essentially a quantitative sense, a mathematical model of Newton's second law, right? That we know is the acceleration is directly proportional to the net force, but inversely proportional to the mass. And what students figure out is that they have a difficulty trying to explain something like an acceleration. A force they can get, right? Pushes and pulls. They can kind of figure that out. But then when it comes to acceleration, they see that they have a harder time trying to mathematically model what an acceleration is. And that's where we find justifies this describing motion unit, because then that leads to how do we mathematically describe something like an acceleration? We know, right, a gapless explanation of that is that, oh, well, an acceleration is a change in velocity over the change in time, and velocity is a change in position over the change in time, right? And that leads then to the acceleration is equal to the net force divided by the mass. But in order to get that describing motion component, that's what we feel justifies this unit. So instructional segment 1 is on describing motions, on kinematics, right? We got displacements, velocities, and accelerations. And then we tie that into also being able to measure the rate of change of the motion of the Earth's tectonic plates as a result as well. There's a really great common question that you see about Hawaii, which was built under a hotspot, and you can tell by dating the dating of the different islands of exactly the direction at which the plate that Hawaii is on is moving, as well as you can calculate its rate based off of extrapolating those times. So next up then we get into instructional segment 2, which is the cause of changes in motion. This is dynamics or forces, right? Again, now we can finally address that Newton's second law, that the acceleration is directly proportional to the net force, but inversely proportional to its mass. In doing so, we can then start to talk too about things like different plate boundaries and what happens there, about mountain building and how that is constructed. This also includes Newton's second law's close cousin, impulse and the change in momentum as well. So we also are going to include impulse and momentum into these ideas as well, because this instructional segment ends with students being able to design, build, and revise something that will essentially cushion, say, well, like an egg, right? Essentially what it's boiling down to is an egg drop. Now there's many variations of that. I've done before like sports helmet drops. I've done landing Martian rover, Martian rover landers and things like that. I've also heard done like you ship a potato chip and students have to cushion that when they go to ship it. Or something like that. So they're building that and modifying that, and that's kind of where the instructional segment ends. All right. Instructional segment 3 then is looking at gravitational forces at a distance. So here's a part where we did deviate from the California standards. The original, or the California framework. The original California framework is forces at a distance. And that's both the gravitational force and the electric force, and I think they even tie in the magnetic force as well. Some of us who was at the course lead teams had done this method before, and we came to the conclusion that it's actually better to put the electricity and magnetism stuff later on in the unit, because if not, you're addressing not only this gravitational forces, this gravitational force, but you're also then you're bringing up charge and the electric field, the magnetic fields and things like that, that you then kind of toss to the side and then don't bring up until later in the semester. So instead, what we decided to do is we took the electric and magnetic forces, put them into second semester, and kept this as gravitational forces at a distance. So the way that we're envisioning this right now is that you kind of can start off with Kepler's laws of motions, having students investigate Kepler's laws of motions, and then leading into Newton's gravitational force equation, right? Newton's universal law of gravity. And there's a great nature of science component too there, showing the limitations of Kepler's laws and how Newton was able to improve upon that. And then also once you got that, you can then look at orbits and orbital motion. You can look at satellites, moons orbiting planets, planets orbiting stars, and you can look at all that fun stuff. But what we also then added in here is we felt it was a good opportunity to add in here was also the construction of the Earth and looking at the formation of the Earth and the evidence that we have to support how we think the Earth was constructed. So all right, there's that. And then instructional segment 4 looks at mechanical energy and its conservation. So the focus here is mechanical energy. This is also a bit of a deviation from the California framework. So it is a focus on mechanical energy. So that means kinetic energy, gravitational potential energy, and elastic or spring potential energy. Those are kind of the big focuses there. And then also the fact that work will change the energy of a system. And so this sequence also, we're looking at this as a more of a hands-on kind of approach to start off with before we get to things like electric potential energy and magnetic potential energy and all these other nuclear processes and things like that. We're starting with mechanical work and changes in mechanical energy. And this ends with another designing, building, and refining device where they're going to build their own mechanical turbine that will be able to spin and lift up some amount of mass. So you essentially have wind energy doing useful work that's moving, that's creating a force at a distance or increasing the potential energy of something. And so students are building that, but it's focused specifically on mechanical energy and work. And that's where the class, the semester ends. And where it starts, this is what I'm excited about this. I thought this is pretty cool. It starts then with electromagnetism and alternative energy. So keep that in the back of your mind that students at the end of last semester, just built a turbine that did mechanical work. Now they're going to look at Coulomb's law, the electric force, right, as well as magnetic force. And they're also going to tie into, right, you get that inverse square law and all sorts of similarities between the electric force and the gravitational force, how they both can be explained by fields and things like that. And then you also get into the magnetic force, magnetic fields, and how a changing electric field will produce a magnetic field, and a changing magnetic field produces an electric field. And that's where the electromagnetism component shows up. And then students go back to their turbine and refine their turbine to try and address how can they use their turbine in order to produce electricity, to generate electricity, to say run something, right? Turn on a light bulb, or however big and ambitious you want to go. And having already done now the investigation on electricity, on electric and magnetic fields, they will have an idea of how a generator works, right? And that's what brings us to this idea of alternative energy. So they're refining their turbines and also investigating other types of alternative energy, such as wind, solar, and we even go into nuclear fission here. If you wanted to, you could probably throw in fusion as well, the Holy Grail, right? But the big thing here is going to be on nuclear fission, where fusion is going to show up when we address the universe at the last unit. So instructional segment 6, this is another one where we kind of diverged a little bit from the California framework. What we did is we essentially split. The California framework combines mechanical waves and electromagnetic waves. We've split them up into 2 instructional segments. So this one's called mechanical waves and earthquakes. So, and as you could probably think, right, our students live in Southern California. They should probably have some understanding of earthquakes and how they work. And it also is a great way to address the point of there being mechanical waves, different types of mechanical waves, and then we're constantly tying that into earthquakes, which also ends with kind of an explanation as to how we can use earthquakes to determine the composition of the earth as well there. Yeah, so that's the idea there. All right. Instructional segment 7 then goes into light and its interaction with matter. So now we're looking at electromagnetic radiation, and we're looking at the students are going to investigate the dual nature of light. Is light, better explained as a wave or as a particle? And they also look at light and how it's useful for us for communication, and how light is absorbed by certain materials, including biomaterials, right? And we're excited to say we're hoping to utilize a lot of the SOFIA curriculum that many of us have been lucky enough to be a part of, and the people at SOFIA has given us the thumbs up that our entire district can now use this curriculum, and so yeah, we're excited to use that as well. Which all of this then leads to stars and the origin of the universe, the last instructional segment. So this is basically looking at kind of starting off with what stars are made up of and how do we know that, right? After already starting with this, or after already ending with our investigation on light, this leads to then, what are stars made up of, and how can we use, use the spectral analysis to find out what they're made up of without even having to go there, and then what does that tell us then about how stars are formed, right? You can go into then nuclear fusion, not fission anymore, looking at nuclear fusion, and looking at stellar evolution, how stars are created, live and die, right? And all the fun stuff like that, which leads to the other fun stuff like supernovas and black holes and gravity waves, and you even get to then go from the get to discuss from the very beginning, the origins of the universe, to the very ends of the universe. I mean, who doesn't want to have that kind of scope and scale in your to end your class? And that's how the class ends. So a big emphasis also is not just on these ideas, but how we know them and why we think the way that we think. So finally, to wrap things up again, that's the unit. Again, we're really excited about it. So again, instructional segment 1, describing motion. Then 2 is the cause of changes in motion. Instructional segment 3 is gravitational forces at a distance. 4 is mechanical energy and energy conservation. 5 is electromagnetism and alternative energy. 6 is mechanical waves and earthquakes. 7 is light and its interaction with matter. And then 8 is stars and the origins of the universe. So again, yes, we're really excited to share this with you. If you have any questions, feel free to stop by during our office hours that we're going to have at the end of the year. So thank you for listening. Take care. Bye.